In the last class, we were talking about the different operators in C programming, and we discussed about the arithmetic operators, then relational operators as well as logical operators we have discussed. In today's session, what we will be discussing is first we will see what is the bitwise operators and if possible the other operators also. Bitwise operators are actually, we said the numbers, the elements or the characters are stored in C programming as bits, as 0 or 1 bits. So that is how it is being stored. That is, the computer understands only the binary formats. That is, if we say that 2, the 2 will not be understood by the computer. Instead, if it is 1, 0, then only it will be understood by the computer as 2. That is in binary form. In binary form, we have to convert whatever is happening, whatever is we are inputting, or whatever data is there that is being used in C programming. It is to be converted into binary format. So bitwise operators are done, or they are applicable to the binary formats or the binary numbers or binary representation of things or the data. So the binary or the bitwise operators are used in programming, in C programming, to perform bit level operations. That is when we are converting it to the things into bit levels, that is into binary format, then only this is applicable. And even if we can use it in the other formats also. That is, we can say that A and B, or we can say 8 and 5, it's okay. But what happens is then 8 is converted into binary and 5 is also converted into binary. Then only this operation will be happening. So that is it. The bitwise operators are these one, the ampersand, the and. We have seen the double and. Double and is the logical and, that is logical and, whether the first one and the second one. So that is it. But in this case, in this ampersand, this is only a single ampersand, that is bitwise and. So there is actually an address of operator is also there, that is also ampersand. If we write ampersand A, this means the address of A, the address of operator, and A and B means A and B. So that is in binary format, A and B. So if it is something like the AND can be used as a unary operator, or it can be used as what is an operator with multiple operands. So here there are 2 operands, and here there is only 1 operand. When there is only 1 operand, the operation is known as a unary operation. So the ampersand can be used as a unary operand as well as using 2 operands. So in 2 operands A and B, this means the bitwise and of the bitwise and of A and B. This represents the address of A, so that we will see later, the address of operator. So then ampersand, then bitwise and. Then this is the pipe sign, as we have seen in the logical OR condition. We were using 2 pipelines, 2 pipes, but here there is only 1 pipe. So this is bitwise OR. Then there is the caret symbol, that is a shift 6. If you put shift and 6, then you will get a symbol like this. That is the caret symbol. That is bitwise exclusive OR. That we will see what is an exclusive OR and how these bitwise operations are done. Then this tilde symbol. This tilde symbol represents the bitwise complement. Then double less than symbol. So that is the shift left. Double less than symbol is the double shift left. That is, we are shifting the characters to left. So that also we will see. Then the shift right, double greater than symbol. So it is shift right. So most of this, see this ampersand, tilde, and not tilde, the pipe symbol, then the less than symbol and the greater than symbol. These symbols we have already used in either as a double format, like ampersand we used in 2 ampersands, then pipe symbol we used 2 pipelines, and the less than shift left. Instead of shift left, we used the less than symbol. That is a conditional, what was it? It is a relational operator. Then greater than symbol, that is also a relational symbol. But when we put 2 greater than symbols together, it is shift right, and when we put 2 left, less than symbols together, it is shift left. So let's see what each operations means. That is bitwise and, bitwise or, bitwise exclusive or, bitwise complement, shift left, shift right, etc. So the bitwise and the output of the bitwise and is 1 if the corresponding bits of two operands is 1. That is, if two operands are there, then the corresponding bits, that is, in this case, see, here is we are considering 12 and 25 as our example. 12 in binary can be represented like this, that is 0, 0, 0, 0, 1, 1, 0, 0. So that is in binary. And 25 can be represented like this, 0, 0, 0, 1, 1, 0, 0, 1. So it is again in binary. In bitwise operations, this binary, this bit as well as this bit, in the case of 12 and 25, if we are doing an operation like this, 12 and 25, an operation like this, so the corresponding bits at the same position, that is 0 and 1, this will be considered. So this is taken as an ampersand, an and. 0 and 1. If both are 1, then we will get a 1. If one of the bit is 0, then we will get a 0. This is like our logical operators, almost the same as the logical operators. But here we are doing the bitwise operations in all these positions. So if either bit of an operand is 0, the result of the corresponding bit is evaluated to 0. So let us do the AND operation of two integers, 12 and 25. So 12 and 25 we are doing. See, the bitwise AND operation of 12 and 25 will give you this 0 and 1. So 0 and 1 means 0. That is, since only if it is only 1 and 1, then only it will be 1. So here 1 is 0, so it is 0. Here it is 0 and 0, so that is also 0. 1 and 0, 0. 1 and 1, so that is a 1. So here it is 1 and 0, so it is 0. So here all the others are 0. So all the three positions become zeros. So 0, 0, 0, 0, 1, 0, 0, 0. So this is equivalent to 8. 8 in the decimal. So the result of 12 and 25 will result in 8. So that is the peculiarity of what you say, the integer, I mean the binary operation or the bitwise AND operation. So while doing the bitwise operation, this is what is happening. That is, the bitwise comparison is done. The bitwise operations are the bitwise AND conditions are taken. Now let us consider the bitwise OR. The output of bitwise OR is 1 if at least one corresponding bit of two operands is 1. So either one of them is to be 1. So we are again doing the same thing as same thing with the 12 and 25. That is bitwise OR with the 12 and 25. For 12, this is decimal 12 and this is decimal 25. So 0 and 1. Sorry, so 0 or 1. This is OR operation. See, this is the OR operation. So 0 or 1, so it is 1. 0 and 0, 0 or 0, so it is 0. None of them is 1. 1 or 0, so it is 1. 1 or 1, so it is again 1. 1 or 0, it is 1. So the rest are all zeros, because here there are 3 zeros and here also there are 3 zeros. So the 3 becomes 0. So 0, 0, 0, 1, 1, 1, 0, 1. So this is it. So it becomes 29. So this is the representation of 29. So 12 or 25 will result in 29. So this is the peculiarity of the OR operator. So when an OR operator is done, mostly in most of the cases, a larger number is, we will get a bitwise OR operator is done, we will get a larger number. When a bitwise AND operation is done, we will get a lower number. It is something like the union and intersection in the case of what you say, the sets. The in mathematics, you might have studied the set operations. There you have studied the union operation as well as what you say, the I don't know, the other operator. So in one we are taking the values which are common to both, and in another one in either of them, the value which is in either of them. So when we are doing the OR operator, the bitwise OR operator, we are getting a larger value. When we are doing a bitwise AND operator, normally we will be getting a smaller value. Then the next one is bitwise exclusive OR, the XOR. It is shortly denoted as XOR, the bitwise exclusive OR. So that is XOR. The result of bitwise XOR operator is 1 if the corresponding bits of two operands are opposite. That is the only thing that is to be checked. Whether the two operands are opposite, then it is 1. If both are the same, then it is 0. So let's see in the case of 12 and 25 what is happening. As I said, this is equivalent to 12 and this is equivalent to 25. So 0 XOR 1. So this is exclusive OR. So both are opposite. One is 0 and the other one is 1. So it is 1. And this is 0 and this is 0. Both are the same. So it is 0. Here 1 or 0. So it is again 1. So 1 and 1. So it is 0 because both are 1. Both are 1 means it is 0. Both are the same digits or the same bits. Then we remove, then we assign 0 value to it. So then 1 and 0 and 1. So both are opposite. So this is 1. So this is the bitwise exclusive OR, the XOR statement. So the condition for 12 caret 25 will give you 21. So this is the bitwise OR. In order to find out these things, you cannot directly find out using the decimal digits. That is, you can either remember it, but always you cannot find out the say 11 caret 25 XOR 25. We directly we may not be able to find it out. We have to convert this one into binary, then this one into binary, then we have to do the bitwise operation, then we have to convert it by to decimal also. Then only we will be able to find out the actual value of 11 caret 25. So then the truth table for the bitwise operators. This is almost similar as the truth table for the logical operators. In the case of logical operators, there was a logical not pair. Here there is a, instead of a logical not, we have a logical exclusive. I mean the bitwise exclusive OR statement is there. So when A and B are zeros, and so A is 0 and B is 0. So A and B is 0. So that is the bitwise AND operator, that is 0. The bitwise OR, it is also 0. The bitwise exclusive OR, it is also 0 because both are the same. So 0 and 1. A is 0 and B is 1. So in that case, A and B becomes 0 because only one value is 1 and the other one is 0. So it is 0. Then A or B becomes 1 because either of these two values, one of them is 1, so it is A or B is 1. Then A XOR B, it is 1 because both are different, 0 and 1, so both are different. So that is A XOR B is 1. Then the next is 1 and 0. A is 1 and B is 0. So again, A and B is 0 because only one is 1. Only A is 1 and B is 0. So A and B is 0. A or B becomes 1 because either of them, that is A is 1. So either of them is to be 1 in order to A or B to 1. So then A XOR B, that is again 1 because both are different. A is 1 and B is 0. So both are different. So A or B is 0. I mean 1. Then A is 1 and B is 1. So A and B both are 1. So A and B is also 1. A or B, since both the two are ones, A or B should also be 1. Then A XOR B. So this is again 0 because both are ones. Both are the same things. So it is 0. A or B is, I mean A XOR B is 0. So that is the bitwise operators, the truth table for bitwise operators. Then there is a bitwise complement or bitwise NOT. It is also known as a bitwise complement or bitwise NOT. It is represented by the tilde symbol. The tilde symbol comes normally towards the left end of your what you say, the keyboard. So the shift, pressing the shift, the keyboard key towards the left of 1 will normally produce this one, the tilde symbol. Then the bitwise complement operator is a unary operator, and works only on one operand. That is a unary operator is which works only on one operand, and it changes 1 to 0 and 0 to 1. That is the condition. So it is say we are converting this 35. We are doing the bitwise. We are finding out the bitwise complement of 35. Then 35 in binary is 0 0 1 0 0 0 1 1. So this is the binary representation of 35. So if we do the bitwise complement as the definition says, so bitwise complement of this one is changed to 0 and 0 is changed to 1. So that is how it goes. So 1 is changed to 0, 1 is again changed to 0, 0 to 1, this 0 to 1, this 0 is also changed to 1, this is 1 is changed to 0, this 0 to 1, and this 0 to 1. So in this case, this particular value, when we find out the corresponding decimal value of this value, then this becomes 220. That is the bitwise complement of 35 is 220. So that is the condition. You might have noticed one thing, that whenever we are whenever we are representing a binary number, we are taking 8 bits. 1, 2, 3, 4, 5, 6, 7, and 8. That is, a byte is taken. 1 byte is used to represent an integer value. So here we are taking 8 bytes, 8 bits in order to represent that particular integer. So that is how this 220 is coming up. But actually what happens is when we find out the bitwise complement of 35, we will be getting minus 36. Let's see how it is being, how we are getting it. In C programming, let us see it, how we are getting it. 1 second. I'll show you the program. So that is the bitwise operator. So here we are doing, this is a program in order to explain the bitwise operators. So here we have defined 2 integers, actually 4 integers are defined, with the integer 1 as integer A. Integer A is 12 and B is 25. Then another integer num, integer num is 212, and I is also something. So here I have put something for the right shift and left shift also, that I comment first. Sorry. Because that we will see later. So this is it. So what we have seen till here is bitwise and bitwise OR, bitwise XOR, and bitwise complement. So A is 12 and B is 25 here. Then into num, and num is defined, that is not up to here, that is for the next condition. The I is also for the next operation. So let us see what is the, here we are printing out the bitwise AND A and B, then bitwise OR A or B, bitwise XOR A XOR B, then bitwise complement of 35. So this is the complement of 35, bitwise complement of 35. And then we do the bitwise complement of minus 12 also, bitwise complement of minus 12. See, bitwise AND, we got 8 in our calculation also, we received 8, and in bitwise OR we received 29. It is same. Then bitwise XOR, it is 21. But here bitwise complement of 35 is minus 36. But when we did the bitwise complement, in our case it was 220. So then how this particular value changed? So here the next bitwise complement of minus 12 is 11. So that is also a difference. So how this particular value minus 36 and 11 comes up. These values are actually obtained by minus of n plus 1. So that is how the bitwise complements are found out. That it can be found out directly from the decimal values itself. If 35 is the complement, then the bitwise complement of that is minus 36. That is 35 plus 1. Then we put a minus in front of it. Then minus 12 plus 1. Minus 12 plus 1 is minus 11. Then we put a minus in front of it. Minus of minus 11 is 11. So that is how the bitwise complement works in C programming. And how this one is happening, let us see. Actually, when we did the bitwise complement of 35, we obtained 220, and then how this 220 is converted into minus 36. Let us see. So we have seen the bitwise complement of 35 is minus 36 instead of 220. But why? The condition is for any integer n, the bitwise complement of n will be minus of this minus had to be here. So this is minus of n plus 1. So this is how the bitwise complement of any integer is found out. So 35 means minus 36. The bitwise complement of 35 means minus 36. To understand this, you should understand the 2's complement. This is based on the concept of 2 complement. So the 2's complement is another operation in the binary numbers. 2's complement is an operation that is happening in the binary numbers. The 2's complement of a number is equal to the complement of that number plus 1. That is, whenever we want to find out the 2's complement, what we have to do is we have to first find out the complement of that number, and then we have to add 1 to it. So that is it. So let us see some of the examples. The decimal value 0. We consider the decimal value 0. Then, sorry. So then the binary value. The binary value we consider, this is the binary value. Since we represent a decimal value using 1 byte, so there will be 8 different positions will be there. That is 8 bits will be there. So here there are 8 bits. And the complement is to be the 2's complement is the complement of this number. The complement of this number we are taking by inverting each of these digits. 8 zeros, they are inverted. So that is 8 ones we obtain. So 1, 2, 3, 4, 5, 6, 7, 8. 8 ones we obtain. And then we have to add 1 to it. We have to add 1 to it. And then we have to put a minus symbol instead in front of it. So that is how it works. So then let us see. Then what happens is 1 is added to this one. So that is 1 is added to this one. So that is 1 plus 1 becomes 0. In the case of binary, it is 0. Then another 0. 0, 0, 0, all the zeros, all the 8 zeros will be there, and the carried and the last digit that is carried is truncated off. So here there will be 8 zeros and a minus symbol is also there. So that is it. So it is minus 0. That is in decimal. So then in the case of 1, what happens is 0, 0, 7 zeros and 1. So that is the binary representation. Then we take the 2's complement. We take the complement of this one, that is 1, 1, 1, 1, 1, 1, 1, 0. So that is the complement. Then we add a 1 to it. So when we add a 1 to it, this 0 plus 1 becomes 1. So that is this particular number, that is minus of 256. So that is the decimal value. That is the 2's complement of 1 is minus of 256. Then 12. 0, 0, 0, 0, 1, 1, 0, 0. Then we add minus of this particular value. That is minus of 1, 1, 1, 1, 0, 0, 1, 1. So this is the the complement of this one. Then we add a plus 1 to it. Then a minus is also inserted. So that is minus. When we add this one, 1 plus 1 is 0. Then 1 is remaining, the remainder is 1. So that 1 is added to this one. So that is also 0. Then another 1 is remainder. So that 0 is added to here. So that 0 becomes 1. So the rest becomes same. The 1, 1, 1, 1, 0, 1, 0, 0. So this is equivalent to minus of 244. So then if we try the 220 is the value that we obtained by finding out the complement of 35. So that value, that in binary it is 1, 1, 0, 1, 1, 1, 0, 0. The complement of that one is 0, 0, 1, 0, 0, 0, 1, 1. Then we add a plus 1. Then we are taking the minus. So that is 0, 0, 1, 0, 0, 1, 0, 0. So this is the minus 36. So that is the decimal. So in this case, in all these cases, the overflow is ignored while computing the 2's complement. Like here, if this value is added, we are adding a 1 to this last, this one also. This one also we are adding a 1. So in that case also a 0 results and a remainder of 1 is there. So that remainder is an overflow. That is towards the left. The 9th bit it has to be considered. So that bit we are ignoring that one. So that is how this becomes 0. So this is how the 2's complement is found out. That is, we are taking the complement of the binary equivalent of that particular number. Then we are adding a 1 and then we are putting a minus symbol also. So that is how it is being done. Then the bitwise complement of 35 is 220, that we have already found out. The bitwise complement of 35 is 220. But the 2's complement of 220 is minus 36. That is how the output of output is minus 36 instead of 220. That is actually what the node, the bitwise complement, the bitwise node operator gives is the 2's complement of the complement of that particular number. That is the 2's complement of the complement of that number. That is how it is being done. So the bitwise complement can be directly found out using this particular relation. That is, the bitwise complement of the number n is minus of n plus 1. So that is the relation. So the bitwise complement of n is the complement of n, then represented in 2's complement form. This value, this complement of n should be represented in 2's complement form. So the 2's complement of n is minus of complement of n plus 1. So that is minus of n plus 1. So that is a bit tricky. That is, the only thing that you have to remember is that whenever you have to find out the bitwise complement of a particular number, it is calculated like this. It is calculated like this, minus of n plus 1. Or if you want to and a bit more detail, it is the 2's complement of the complement of that number. So that is how it is being done. So that is about the bitwise complement or the NOT operator. Then there are two operators, the bitwise right shift as well as the bitwise left shift. The bitwise right shift operator shifts all bits towards the right by a certain number of specified bits. That is how it is being done. So it shifts the values towards the right, shifts the bits towards the right. Let us assume this is a binary number, that is 212 is converted into corresponding binary number 110101000. So this is the binary equivalent of 212. So if we do an operation like this, 212 right shift to 2, then what it does is 00, then 110101. This is how it results. How this one is resulting is we are shifting all the digits towards the right by 2 positions. So see, this 11, this 11 is coming up here, 2 positions towards the right. This 01, then 2 positions towards the right, 01. This 01, 2 positions towards the right. So again then these two zeros, the last two digits, they are truncated, they are removed. So that is the right shift by 2 digits. When we are doing the right shift by 2 digits, we are truncating or we are removing the rightmost 2 digits and we are inserting 2 zeros towards the left. So if we do 212 right shift 7, so it has to be shifted by 7 digits. 7 digits means we have to put 7 zeros in front, and then we have to start writing this particular number. So only one can be written. So because all the 7 digits after that particular number, these values are to be truncated. So that is how the right shift works. So when we does 212 right shift 8, it will result in 0 because 8 shifting means 8 zeros will be inserted. So that is all the bytes, all the positions within that particular byte will be filled with the zeros. So the answer will be 0. So if we put 212 right shift 0, then we will be getting no shift because no value is shifted towards the right. So that is how the right shift works. Then the bitwise left shift. In the case of left shift, what the operator does is it shifts all the bits towards the left. All the bits is shifted towards the left, and the positions that been vacated, that is being that has been vacated by the left shift will occupy will get a value 0. So that is how it. So like this 212 is again we have done. So 212 left shift 1. So what we does is we does a particular value left shift additional 0 is inserted here, additional 0 is inserted here, and since so this is the condition, an additional 0 is inserted here. So while by finding out this particular value, this particular while doing the left shift, the none of the values are truncated actually. This is the 9th bit actually. So this is the 9th bit. 2, 4, 6, 8, and 9. While doing the left shift, we are not truncating the values, but while doing the right shift, we are truncating the values. So that is how it works. So here, when we are doing the left shift, one is all the digits are shifted towards the left by 1 position by doing this operation. So here we will be inserting a single 1 towards the right. And if it is 212 left shift 0, that means there will be no change in it because no positions are to be inserted. But 212 left shift 4, we have to insert 4 zeros towards the right. We have to insert 4 zeros towards the right. That is in binary. And if we convert this particular value into decimal, it will be 3392. That is it. So that is, it will get a very large value, 3392. Now let's see how the right shift and left shift works in different in C programming. So actually what we have commented in the previous session that we can remove, and we can remove these positions. We can comment these positions. Yeah, okay. What this takes is it takes the num value is taken as 212, and then there is an integer I is there. So what we does is for I equal to 0, I less than or equal to 2. So that is I is 0, I 1, I 2. That is happening. Then we are shifting the value, the NUM, the value of NUM, right shift I is taken. So the right shift by 1, 0, 1, and 2 is being done. So here, the next in this case, the left shift, NUM, left shift I. I is 0, 1, and 2. So the left shift 0, left shift 1, and left shift 2 is done. So let us run the program. See, when the 212 is right shift by 0, it is 212 itself. When it is right shift by 1, it is 106. When it is right shift by 2, it is 53. When it is left shift by 0, it is 212 itself. Then left shift by 1, it is 424. When it is left shift by 2, it is 848. So this is how it works. So let's change the value of I from 2 to say 5. So what the values we will get, let's see. So when it is right up to 2 we have seen. When 212 is right shift by 3, it is 26. Right shift by 4, it is only 13. Then right shift by 5, it is 6. So when it is left shift by 3, it is 1696. Left shift by 4, it is 3392. And left shift by 5, it is 6784. Can you find out any relation between these numbers? Actually, what happens is it is on each shifting, it is dividing by the integer division by 2 is being done. So 212 divided by 2, that is 106. 106 divided by 2, it is 53. 53 divided by 2. 53 divided by 2 is 26 because it is an integer division. Since integer division, the fraction will be discarded. So it is 26. Then 26 by 2 is 13. 13 by 2 integer division, it is 6. So that is the right shift. That is actually what we are doing in the right shift is we are dividing each number, the integer division. The integer division is done by 2. And in the case of left shift, what actually we does is we increase or we multiply the number with the 2. 212, 424, and 848. Then 1696. 3392, 6784. We are multiplying each number with 2. So that is the condition. So if we left shift by 5, it means 212 into 2 raised to 5. So that is it.